I welcome Sunil, and you have 30 minutes for your presentation.
Okay. Thank you, Sumesh. And let me begin by thanking Ashish and the whole team here for giving me this opportunity to address this learned audience about some work which I've been doing. As the previous speaker said, it's something from the past and something, which is we are doing now. And of course, there's not many surprises here, I think. So this is mainly on dynamics of active polymers, and I show this picture in the background because this is the only one I will show from biology, I guess. And this is to show the motivation for doing such active polymer modeling. As you see here, this is the actin filaments in a cell, and the cell is full of such filaments, and they are active because of the reason of molecular motors moving on it, which I will come to in the next slide again. Okay, so that's the basic motivation for the thing. So I show here a few things. So one of the thing is, like people do these experiments in which they take a cell and then they hold it between two cantilevers, and then they can do various mechanical experiments on this, okay, dynamical experiments, and then they would try to understand this response of the cell. And the cell is being an active object, okay, would respond actively, and we need to understand how that active mechanism is coming in, right? And there is another thing here in which a cell is crawling, and this crawling motion again involves a lot of rearrangement of the filaments inside, and mostly it is, or these kind of crawling is driven by such mechanisms, right? And then there is also in vitro such systems which people have now made in the laboratory, where you can have biopolymers and biological motors together, and then they can exhibit very, very interesting patterns, right? So now what's common in all of this is that they all involve they all involve some sort of filament. I'm here showing a cartoon movie of on a microtubule and a motor working on it, right? So it could be all of this involved. This is actually microtubules, and these things will involve mostly actin filaments, okay, and in which some motor is working. Okay, so that is what we are trying to model, okay, in this thing. Okay, so how do we model that? If you take a filament, okay, and you have a motor on it, okay, and this motor is now, and this whole thing is in a solution, okay, and now the filament motor as it walks, okay, it exerts a force on this direction on the filament, and there is a cargo which is attached to it, or it is moving in the fluid, so there is a force acting on that direction. So and these forces are generated, of course, from chemical energy being converted into mechanical force, right? So there's like ATP or GTP, right? Okay. So now you have, if you consider this volume, and then that is like this volume, then the net force is 0. Okay, and the simplest way to model that would be like a force dipole. Okay. Now this force dipole in this volume, so this is model. Okay, and now if you take a polymer as many motors working on it, of course we consider the simplest case of your continuous stream of motors working. You can also think about disorders, etc. later, which I will not consider here. Okay, and so in this case, you can think about this polymer now having many motors working on it as a string of such force dipoles. Okay, and the force dipole, when the force is in this direction, the forces are in this direction, you would call them as extensile, and when you're in this direction, you call it as contractile. Okay. Okay, so now this is the model which we are looking at. Okay, we are looking at the dynamics of a polymer which is made of such elements. Okay, and now these kind of polymers can also be constructed from synthetic nanoparticles like the gold and platinum nanoparticles here they're shown. Okay, and you could have these also exerting forces similar way. Okay, and you could have a polymer made of this. Okay, and which also has been done. Okay, and yeah, so I will. I think there is a reference to that. Okay, it will come later. Okay, so now, if you consider a filament like this, and then the net energy in the system is you coming from the springs and coming from a bending modulus. Okay, so we consider this as a stiff filament. Okay, because biopolymers are stiff in some scale. Okay, so they are stiff filaments. So there is some bending modulus in that, which gives it a persistence length. Okay. And then there is for self-avoidance of this polymers. Okay, that's a term which would be there. And then spring is, we took it as a harmonic spring in this case, and the bending modulus is modeled as a three-body interaction which is coming from that. Okay. Okay. So now, if you consider such a force, the nth bead, any of the bead would experience a force which is coming from the conservative, the conservative force which is coming from this potential, right? This is standard. Okay. And in addition, then you will have this force dipole contributing a stress in the system. Okay. So now this is what we have to solve, right? This is considering that. Okay. And this was done some time back, almost a decade back by us, and then this is okay. This is the reference for this kind of polymers where you can string them up and then you can make an active polymer. So active polymers need not come only from biology, or it can also be synthesized. And I guess this would get better as the years go by. Okay, so now if you have a string of polymers like that, and the velocity of that is now given by, that is an OC tensor. We will be looking at a very low viscosity regime, high viscosity regime, right? And the velocity is given by the OC tensor, this time incompressible fluid, okay? And for when you have a stress term, okay, and then that would be given by this propagator d alpha beta gamma. Okay, so this is standard equations, okay, and now we solve this equation of motion. Okay, this is okay, so that is what the most of my talk is about, solving this equation of motion. We will the actual nature of this would change a little bit with boundary conditions, which I would mention as I go along. Okay, now now there are two time scales in this problem which you can think about. One is the elastic relaxation time, okay, and other is the active relaxation time. Okay, there are two things coming from this. Okay, the activity, which is the strength of that force dipole, and that will give you one relaxation time, which is controlled by that. Okay, and other relaxation time come from the bending modulus of the system. Okay, so this is 2, and you can actually come up with a number which is the ratio of these two, even though that is p. I might use this to just parameterize my plots, but otherwise it's not nothing more intuitive which we can get from this number. Okay, oops, what happened here? Right. So just to give you an idea about what this number and the real system would be, and it is like this, that if you take a filament of length about 30 micrometers and which has a bending modulus of kappa, which is 50 piconewtons per micrometer square, and then if you have 200 motors per micron exerting a force of 6 piconewton, then you will get this about 60. Okay, that just to give you a feel for the number. Okay. Okay, so now if you take an initial filament like this, okay, and this is a 2D simulation. If you take a filament like this, okay, and if you let it, and there is each of these beads, you remember, are made of these force dipoles, okay, and that's the flow it will set up if it's a straight filament. Okay, now if you perturb this filament with some deformations of the wavelengths, okay, and then you can get something like that, okay, and this is the way the flow would be. And as you can see that, wherever there is a bend, there is a net flow in that direction, right, which usually comes from that thing, okay. So even though the straight filament is like stretching, okay, it is only a stretching along the filament, it's a stretching, okay, but if you have a small bend on it coming from other fluctuations, okay, and then you will have a net flow coming in that, and that uncompensated flow would then just drive this filament, okay, and then you can see that if you have a filament like this, and then there is an uncompensated flow, and it will just drive the filament, okay. And that filament would then the counteracting force would be only the bending modulus, okay, so that's what you would see. Okay, so now for all filaments we can show this are unstable for length greater than kappa by sigma naught. Okay, this can be shown. Okay, and then the filament will move in the direction of the bend. Okay, yeah. So now for the rest of my talk, I would replace these beads with just a continuous filament, just for clarity. Okay, and then that would be a straight filament will have a flow like that. As you can see, it's stretching. Okay, and if you have a bent filament, then there is a flow in that direction. Okay. Okay, so now I'll just switch gears and go into multiple of these filaments. Okay, I'll take many of these filaments. Okay, and put them in a confined volume. Okay, so I would consider confined on the surface of a sphere. Okay, and confined on in a volume. Okay, so I took my theoretician's freedom to just say that this is a rigid confinement. Okay, and but the flow is three-dimensional unconfined flow. Okay, but the polymers are confined. Okay, so it could be like confined in optical trap or whatever. Okay, and I won't allow so there is this confined by a potential, and in both cases, but the flow is unconfined. Okay? And then I would look at what I can see, right? And if it's in low density, and then I would see that these polymers actually move around, and what is shown in color here, the different color, is actually the curvature. The red would mean more curvature, and as go lower down, the green is less curvature. Okay, so that's what you could see, that you can move around in this. Okay, and this is about A equal to 30, and this is the volume fraction of the polymers which I have. Okay, and as I go into higher density, okay, I get entanglement. Okay, so I will see that this chain gets entangled. Okay, and then it moves as one mass. Okay, and this is coming primarily from the hydrodynamic interaction between filaments. Okay, so there are two things is happening here. One is a filament, because of the activity, the filament gets driven. Okay, and then there is a hydrodynamic interaction between the filaments, which makes them stick to each other, and then they get entangled above a certain concentration of the filaments. Okay, so I can characterize this. I can look at contact, the correlation between autocorrelation between two different beads in two different polymers. Okay, and then I can plot those things exactly as a function of activity, that is the strength of the dipole, for a fixed concentration, or for a given activity as a function of the concentration. Okay, and then you can see that as you increase the activity, okay, the autocorrelation function decays slower. Okay, showing that there is entanglement coming in here, and similar thing which you can see here also in this case. And that as you increase the active concentration, okay, it gets more and more entangled. Okay, and then there's no entanglements in this. One can characterize that entanglements, etc. I'm not going into all of this detail here, just to show you that the time scale, coming from those correlation plots, okay, as a function of activity, if you look at it, it kind of diverges at some activity. Okay, and similarly, I can do that for the concentration also, and then you can make a kind of a state diagram from that, and which shows a disentangled and entangled thing as a function of the activity and the function of the concentration. Okay. So this is for the volume confinement, if you do. Okay, and now if I can also look at this on a surface confinement. Okay, so now I have these polymers which is confined on the surface, again for different concentrations. Okay, sorry, I didn't write that concentration here. Okay, but as we increase the concentration, again you can see that for lower concentration they actually move around baristically. Okay, but then there is a nematic transition at a higher concentration, and then it moves into now this is now showing a nematic phase. Okay, and with spontaneous generation of plus and minus defects. Okay, and then these defects coalesce, but then they generate more of them, etc. So this is an active nematic polymer in this particular case. Okay. So but then one can look at this transition of this as again as a function of now concentration for a fixed activity. I'm plotting that here. And now also as a function of the bending modulus. Okay. As you decrease the bending modulus of this polymer, okay, you will get more and more defects generated, and the nematic phase kind of disappears because there's so many defects generated. So this nematic phase actually kind of melts by generation of defects in this case. Okay, so there's a whole lot of defects. Okay, so that is one, and now I wanted to just switch gear and then to talk to you about something different. Okay, but again on active polymers. So now what we see is that you could these active polymers. Oh, sorry. Okay, just okay. Okay, I can model this now active polymers. Now I'm doing this active polymers now, and this is my active polymer, and now that is now stuck on a big bead. Okay, a big bead, and which is passive. Okay. Now it's like a colloidal sphere. Okay, and I have this polymer. Okay, and I'm sticking this polymer into this colloidal sphere. Okay. And now there's a slightly different formalism here, but it is almost same thing, but in a slightly different formalism in the sense that now the activity is modeled by a slip velocity on the surface on all of these beads. Okay, so all these yellow beads are active. Okay, and this is a passive bead. Okay, and that's modeled to a slip velocity, and so the activity is now defined as in terms of that slip velocity which we put in. Okay, so apart from that, it is very similar. Okay, now you have that equations of motion for both the colloid and for the equation of motion for the active bead. Okay, and so this passive colloid would now experience a torque. Okay, and also a force due to the motion of this active filaments. Okay, now the interesting thing is what is that if you take that filament, okay, what I earlier shown, that just an active filament. Okay, and which is moving around in the direction of the bend, okay, and interacting with other filaments. Now, if you take that filament, if you clamp it, okay, if you clamp it means that you actually stick it to the surface, but also with the a normal direction there. Okay, so it's clamped. Okay, so that's what I mean by clamping. Clamping means that it is this end is actually fixed vertical. Okay, right. And if you fix that, if you clamp it, and then if you solve the equation of motion, you will see the two different regimes, actually three different regimes. You will see a quiescent regime in which nothing happens, the filament remains straight, and then there is a flow around that. Okay, and then as you increase the activity, you see that this filament is unstable to corkscrew kind of motion. Okay, beating. Okay. And if you further increase activity, this corkscrew motion then will go into this limit cycle, move to another limit cycle, which is the planar motion, beating motion. Okay, and that's what I was trying to show you here. Okay, so this is the corkscrew kind of motion, which when you are in this regime, there's a fixed filament here. Okay, and then that kind of moves in a corkscrew fashion here. Okay, and then if you now increase, if you go into this regime here, and then you will see that it kind of do a planar beating. So, it's like you must have seen this bacteria and other cell organisms, they have this flagella, and then they also have this cilia. Okay? So, the one is like a cilia-like motion, another is like a flagella-like motion. Okay? This is more like a flagella-like motion, and there's a cilia-like motion on the thing. Okay, and that's what you see. So, now this is what made us think that, okay, now what happens if this is the flow which can generate. Now, what if I stick this end perpendicular to into a sphere? Okay, that is a passive sphere, as I said. Okay, and now if I do that, okay, and again I will get this three kind of motion. Okay, I will get this linear state. Okay, in which the bead is now just propelled in one direction. Okay, in the upward direction, and then there is a helical beating regime which is coming from the corkscrew motion. Okay, and in which it propagates that direction, and then you can have a planar beating regime depending upon what the angle is. Okay, and then you can actually look at the whole phase diagram, and you can see where it goes from one state to the other state. Okay, and you can characterize the velocities also using the parameter here. Actually, the main parameter which controls here is the bead size. That's the BC, which is called the colloidal bead diameter divided by the size of the active beads. Okay, so that is one of the parameters which we use here, and other parameter. But there is not much dependence on that. But then there is an activity is another parameter. The thing. Okay, there are some surprises here also. In this case, I will just show you this movie. Okay, let the movie run, and then show you that this is what I showed you, that now we are in this regime. Okay, when we are in this regime for low activity, you have the straight filament. Now this movie is shown in the center of mass frame of the colloid, so you don't see anything. And here you will see the helical beating regime. Okay, and in which the filaments are beating in a helical fashion. Okay, and then there is a regime in between this to the planar beating. Okay, where you have with this regime now, where you have helical beating with periodic switching of the sign. Okay, so it's periodically switches. Okay, in this case, of course, this is I would still say that an idealized system in the sense that I have these polymers are all without any defects. Okay, and so you see a periodic beating of the thing, and it kind of switches the sign of the helical beating direction. Okay, and yeah, you can see that is watching the shadow, that it is switching from one to another one. Okay. And yeah, I can't speed up this movie here, unfortunately, I think. So you will see that when it moves from, after that it moves into a planar braiding regime here, okay, and yeah, so now it switched to the planar braiding regime, and then there is, yeah. So basically, it is going through these regimes as we increase the activity here. Okay, that is what I'm taking a cut through this. Okay, and then you have a kind of a sculling kind of motion. Okay, where it goes from one right to left, etc. Okay, so this is like a sculling. Okay, so you have all of these modes of swimming for these things. Okay, so now if I could also then think about just for the fun of it, that you could think about what happens if I take two of these filaments and stick to a bead, okay, instead of one filament, right? Because there is also coupling between these filaments, okay. And now it turns out that it actually depends on the angle at which you stick them, okay. And if the angle is sticking two, then it will move in this kind of synchronized fashion, okay. And you can also show that as you change the angle, you could also get motion like the chlamydomonas and things like that. Okay, and yeah, so that is one. So I think I will now because I'm running out of time. I have 10 minutes.
Yeah.
10 minutes. Yeah. So in the next 10 minutes, I wanted to show you something which we are doing with this now in this active polymers, and that's about putting them in shear flow. Okay, because we wanted to understand. As I said, the final idea is to understand the rheology of an active concentrated suspension of these polymers. Okay, so we wanted to first characterize the rheology of one of them. So there was one filament. Okay, the response of one filament to a simple shear flow. Okay, and that is what these movies show. Okay, so we'll put it in. Oh, this is playing in some random order. I'm sorry, but yeah. So we can see that as this is for a low shear rate, and this is for a high shear rate, and this is for no activity. These are passive polymers, okay, and these are active polymers, okay, and below, okay, and this is characterizing my activity number, sigma naught. Yeah. So as you can see that this is a passive polymer at a high shear rate, okay, and there's a low shear rate, and then they tumble, okay. That's what the motion is well known. It's a semi-flexible polymer in a shear flow, okay, which has been well studied earlier, okay. And you can see that they actually tumble. They tumble very slowly, okay. And but then if you have high activity, they tumble faster, okay. But then high shear rate. But okay, maybe I should just go there and then. So let's look at these two. Okay, there's a high shear rate, and you can see that the way it tumbles, okay, changes as you are changing your activity. It's the same shear rate, okay, but when I change the activity, it tumbles, it changes. It kind of tend to stay more in an extended state here. See, this kind of state is more stabilized, okay, and in this case also you can see that this is in the case of no activity, okay, and there is a very slow tumbling, okay, but there is more coupling in the shear direction, but still it's very very slow. Tumbling, because you remember the shear rate is in that direction, so it has to tumble that way. Okay, so it takes a long time to tumble. Okay, while when you increase the activity here, the tumbling becomes a little faster. Okay, so what we see is that as you increase the activity, okay, for low shear rate the tumbling becomes faster. Okay, and for high shear rate the tumbling becomes slower. Okay, so now if I plot the tumbling time, the tumbling interval, okay, as a function of the shear rate. Okay, in this case I will put a particular number, and then what do I see is that for no activity case I will get a 3/4 line, which is very well known. Okay, so people have done this long. Okay, and this is the 3/4 line you will get. Okay, that's a red line here, and as you increase the activity, you will see that for low shear rates, okay, you get the tumbling interval to be smaller. That means it is tumbling much faster. Okay, and for higher shear rate, it's tumbling slower. Okay, and now this is you can show that for different stiffness and there is a point at which it crosses over this line. Okay, this red line. Okay, which is that no activity line, and it crosses over at a point which is kind of independent of the activity. Okay, So it just seems to be crossing over at a particular value of PE, a particular number, which is independent of activity. And then you can see that for the case of, as you increase the bending stiffness, okay, this number goes, this moves down, the activity required to do that. And we believe that this is actually coming from a competition between the active forcing, okay, coming from the bending energy, okay, relaxation, okay, and the shear stress, okay. So, and the activity doesn't really play a role in this chain, okay? And you can actually get that, but we are still trying to characterize this number. This is something which is ongoing right now, okay. And now, before I end, I just wanted to show you something which we are currently doing again. That this is that, you know, as I said, our aim was to really look at a very concentrated solution of active polymers, okay. And it turns out that these simulations are pretty expensive, okay, and also that at high concentrations, maybe activity doesn't play all that much. Sorry, the hydrodynamic interactions may not play such role. So we were wondering whether we could kind of simplify this model, okay, and make it into something which is a dry polymer model, an effective dry polymer model. And with that, we have also seen in our simulations that if you look at the motion of these polymers, as you said, they kind of bend and they move, okay, and you've seen that the motion of these polymers actually is proportional to actually it follows the curvature, okay. Now here what I'm trying to plot is the green color is actually showing the curvature, okay, and the green color is showing the black line is showing the curvature variation, okay, and the green color is showing the center of mass motion from the simulations, okay, and you can see that they follow each other, okay, they follow each other for all activity, okay, and since they follow each other for activity, so we thought, okay, one way of doing this for single polymers, I can take now instead of doing all those hydrodynamic interactions, I could just write down an effective model, okay, in which now I have no hydrodynamic interactions, and the forcing is coming only from this curvature dependent active force. So now I replace my whole activity with just saying that, okay, I have a force which is in the direction of the normal, that is the direction of the curvature, okay, local curvature, okay, and I can look at that and characterize that, etc. And I have 2 minutes.
5 minutes.
I have 5 minutes. Okay, then I don't have to rush. Okay, so this is what we see, that you can have you can write down this equation of motion now, okay, and with the active term here, okay, and we can define an activity number, etc. in this case, okay. So now I look at again, I call that as a dry active polymer model as compared to an extensile active polymer which we saw. Okay. So this is a hydrodynamic case, and this is the case of the dry polymer, and you can see that as they evolve, okay, they kind of evolve very similarly. Okay, even though I don't know how to map these numbers from the activity here to here, okay, but you can see that they actually move very similar way. Okay, so this has been encouraging that you can get a similar motion, and we wanted to now characterize it further. Okay, so we are looking at all the single polymer characterization things like end-to-end vector and tangent correlator, etc. Okay, but I'll not present that here for the lack of time. Okay, instead of that, I'll just show you how this would again will show in the case of shear flow in the tumbling interval. Okay, so in the passive polymers, as I said, we recover this 3/4 line. Okay, now this is now plotted as a function of Weissenberg number. Okay, and with scale with this thing scale with the polymer relaxation time. Okay. And I can do that now, I can show you for this active polymer case, okay, active polymer case as you change the activity. Now this is the dry active polymer, okay, and in this case, this is the coefficient which is sitting in front of the curvature term which is driving it, okay, and so now I can plot that, okay, as a function of tumbling interval as a function of those activity, of the shear rate, okay, for different activity, and you can see that like the passive, like the wet polymer, the extensile active polymer which you saw, here again similar behavior, that it is a dry case also, that it shows faster tumbling for low shear rates, okay, and slower tumbling at high shear rates. Okay, so even under the shear flow, this seems to behave very similar. Okay, these two things. Yeah, And so that is, now we can also do the scaling like this, like a passive polymers. We can scale it with the polymer relaxation time, and it, interestingly, it shows that actually for all active cases, it collapses onto one line, okay, and it's still okay, but at a line different from that of the passive polymer, okay, and which is above that. This is what we see. Okay, so this is for a particular beta value, okay, and so basically the scaling law is not changing, okay, but this behavior is changing. It's mainly because in the low shear rate regime, the activity induces more and more curvature, okay, and the curvature allows the polymer to couple strongly with the shear flow, okay, because it's a curved system, okay, and hence the tumbling time goes down, okay. But as you increase the shear rate, the polymer actually tends to remain straight, okay, because of the shear flow. And its ends fluctuate, and whenever end fluctuations are on the both ends fluctuate together, and they get pulled because there is active force going in the direction of the curvature, okay, and hence it tends to remain straight even longer time for the activities. Okay. So I think that is all I wanted to again show you that this comparison between these two plots. Okay, this if you look at this and if you look at this, they look similar plots, except that the numbers are different because we don't have the exact matching between this activity and that activity yet. Okay, so I'll just summarize it here. Okay, and so what we are trying to do. Okay, we have a model for an active polymer which we can use to, or at least our aim is to finally use it to understand the network of such polymers and its shear response. Okay, and much more work to be done, like a coupling of these polymers, cross-linking, and etc. has to be done still. Okay, and with that, I will stop here. Thank you,
Sunil.
From a force field consideration, there should be also an angular velocity. Means if I'm thinking parallelly just from force field. So do these active polymers also sense such angular velocity, reorienting themselves as they come closer?
Yes.
And if now they are near a wall, will there be then a preferential attachment to a rigid wall?
Okay, good question. So the answer is that yes. If an active polymer, this force dipoles. Okay, so now depending upon if it's a rigid polymer, it's easy to say, right? With a rigid polymer, and if you have extensile forces on it, okay. So the force dipoles can be two types. So they're called extensile and contractile, right? So if they're extensile, they have an attraction which is parallel to each other, okay. And if it is contractile, they have an attraction which is perpendicular to each other. Okay, so I didn't mention all of that thing. So that can be seen very easily in rigid polymers. Okay, and that is one of the reasons why you get this entanglements of this polymers. Okay. Now closer to the wall, yes, it's more complicated because then you have to take the wall boundary conditions into it. Okay, and they can tend to align parallel. Okay, and it's interesting because what do you call the coordination between multiple filaments, okay, if you have them, okay, and the closer to the wall can turn exactly the opposite from that in the bulk, okay. So the wall does have a minimal effect, but I can't just explain to you in such short. It's a long answer, okay. So short answer is yes, wall does have a very strong effect.
And one more question, if I may. So for the shear flow, do the active polymers, I was seeing the active polymers were not sensing the direction of the vorticity of the flow. So there was no rotation like in the plane of the presentation.
No, they do.
They do. So they can sense the vorticity, just like what I will expect.
The case which I showed you where it's bending and moving is a very special case of very infinite flows and very symmetrically placed and things like that.
So it's very much like what I can expect from Faxon's laws for rigid particles.
Yeah, rigid particle, right? Yeah, you can have rotations also in this case. Right.
Thank you so much.
Yeah.
Polymer plays a very important role in drag reduction, right?
Right.
Yeah, it is far from away from the wall. It's free shear flow. So, I mean, does this active polymer or passive polymer? I mean, the theoretical explanation is still missing. Why is it so the drag get reduced? So does this explain?
We have not explored. Actually, just a few days back, I was giving a talk somewhere else, and I was got the same question: whether what would be the effect of these polymers in changing the drag and also changing the turbulent regimes, etc., etc. Yeah, we have not looked into it. Yeah, fine. Thank you for that. Yeah.
Hello, sir.
Yeah. Go
Sir,
ahead.
are your model inspired from natural beating mode or whether it is a stochastic?
I didn't understand.
Are your model inspired from natural beating mode? You have shown the polymeric, that means a flagella
Yeah.
was beating around that.
Oh, you are asking, is it different from the actual systems which like bacteria which beat?
Whether
No,
it
no,
is a
that's much more different. Yes, of course. You know, the flagella is a combination of many filaments, and then they slide past each other and things like that. Okay.
Yeah.
And so the beating modes are completely controlled in a completely different way. Yeah. And they have an internal control for the frequency and all of that. But these hydrodynamic interactions also might play, because it is known that, for example, the Chlamydomonas, when it swims, okay, and it has very different modes of swimming, okay, and which of course it might be controlling internally. But when it goes close to a surface, like this question was, when it close to a surface, okay, it's these two filament coordination changes. Okay.
Yes, sir.
And that could be purely aerodynamic, right? So that could be a combination. Okay, but this is just showing that, you know, if you want to mimic and you want to synthetically make something beating, you can do it this way. Okay, but this is not what the living organisms use.
Oh,
Yeah.
thank you, sir.
Last question.
My question goes a little bit in a similar direction. So you've had the clamped filament, and you show the helical motion. If you take several filaments close together in this regime, do they in any way coordinate? I know
They
it's different.
synchronize, yeah.
And do you then overall get more torque transferred to the fluid? Does it
We
enhance
have
or not?
That we have not looked at. We have put only up to two filaments on the surface. Okay, we not put more. Okay, and it gets very expensive, so we have not done this yet. But if you put it on a plane or on a line, all these filaments, and they synchronize.
And then they become a super coiled helix.
Or close to each other. That we have not done. Okay, then they can entangle, and then they
Yeah,
can.
that would be interesting.
No, I have not done. We have not done that.
Thank you.
Yeah, thank you.
Okay, with that, we'll wind up the session. Yeah. So thank you, Sunil.
Thank
we
you.
have a token of appreciation.